Hello everyone, this is the Professor Ricardo Explains channel. Let's solve another problem of classical mechanics by Goldstein. Before solving the problem, let me tell you that we have a playlist for the solutions of the Goldstein's classical mechanics problems. Help our channel subscribing and becoming a member. You will get access to exclusive members-only videos. Your like is also very helpful for our channel to continue helping students all over the world. And let me thank recent members of our channel. Thank you for your support. Okay, Chapter 1, Problem 13. Rockets are propelled by the momentum reaction of the exhaust gases expelled from the tail. Since these gases arise from the reaction of the fuels carried in the rocket, the mass of the rocket is not constant. This is the key information in this problem. But the mass decreases as the fuel is expanded. And our first goal is show that the equation of motion for a rocket projected vertically upward in a uniform gravitational field, neglecting atmospheric friction, is m dv dt equals the negative of v prime dm dt subtracted by mg, where m is the mass of the rocket, the mass which is not constant, and v prime is the velocity of the escaping gases relative to the rocket. And of course, v is the velocity of the rocket. Then, we need to integrate this equation to obtain v as a function of m, assuming a constant time rate of loss of mass. And then show for a rocket starting initially from rest with v prime equal to 2.1 meters per second, so v prime 2.1 meters per second, and a mass loss per second equal to 1 over 60 of the initial mass. We need to show that in order to reach the escape velocity, the ratio of the weight of the fuel to the weight of the empty rocket must be almost 300 factorial. No, I'm joking. Just 300. 300 is already a huge number, as we are going to see. This is just an exclamation point, of course. So the first goal, show that the equation of motion for a rocket projected vertically upward in a uniform gravitational field, neglecting atmospheric friction, is given by this expression here, where m is the mass of the rocket, v is the rocket velocity, and v prime is the escaping gases velocity. Well, we see that m dv dt is the resulting force on the rocket, and it is equal to the time rate of the momentum given from the expelled gases, and this negative sign shows that the force on the rocket is opposite to the direction of the velocity of the gases, or is opposite to the momentum of the gases relative to the rocket, subtracted by the gravity force, mg. Solving this derivation here, we get the negative of dm dt times v prime subtracted by m dv prime dt. Okay, but dv prime dt is 0 because v prime is constant. We already know that v prime is constant, so we do not have this term. And we obtain that m dv dt is equal to the negative of v prime dm dt subtracted by mg, which is the expression we want to show. Okay, now integrate this equation to obtain v as a function of m, assuming a constant time rate of loss of mass, a constant time rate of loss of mass. And since we want v as a function of m, let's rewrite dv dt, which is here, let's rewrite that as dv dm times dm dt. And let's use this result on this equation. Instead of dv dt, let's write dv dm dm dt. If you divide both sides by m dm dt, on the left-hand side, you will get dv dm only. And here, in the first term, it will be the negative of v prime over m, dm dt will cancel out with dm dt, subtracted by this m will cancel out with this m, so it will be g over the ratio dm dt. Now, if we integrate this equation on m, let's write it as dv equals the negative of v prime over m dm, and this other term, g over dm dt dm. Let's integrate that, and we have an integral on v in this side, and these two integrals on m. The limits on this integral are v0 and the velocity v. And we know that the result of that will be v subtracted by v0. But since in the next slide we will consider the rocket starting from rest, let's already use v0 equals to 0. So the result of this integral is just v. This first integral here on the right-hand side of the equation will give us the negative of v prime times the logarithm of m. And these are the limits, m0 up to m. So when the velocity is 0, the mass of the rocket is m0. And we know that this m0 is going to be the mass of the empty rocket plus the total mass of the fuel, subtracted by g over the mdt. This is a constant ratio, so it will not enter, it will not be inside the integral. And the result of this is just m, and these are the limits of the integral. And the final result will be v, and let's emphasize that this is a function of m, equals to negative of v prime logarithm of. So here we will get the logarithm of m subtracted by the logarithm of m0. And that is the same as the logarithm of m over m0, subtracted by g over the m dt, multiplying m subtracted by m0. And our last goal is to show for a rocket started initially from rest, so v0 is 0 as we already considered, with v prime equal to 2.1 meters per second, and a mass loss per second equal to 1 over 60 of the initial mass. That we need to show that in order to reach the escape velocity, the ratio of the weight of the fuel to the weight of the empty rocket must be almost 300. So from this, we can write that v prime is equal to 2.1 meters per second, and the mass loss per second, which is dm dt, this ratio here, dm dt, is equal to 1 over 60 of the initial mass. And of course, this is a loss rate, so there is this negative sign here. What is the escape velocity? Well, we have already calculated the escape velocity from Earth in the previous problem, problem 12. There is a video on that in our playlist, and the value considering no atmospheric friction is 11.2 kilometers per second. That is the escape velocity from Earth. What else? Let's consider ME as the mass of the empty rocket. MF is the mass of the fuel, And m0 is the initial mass of the rocket, which includes the empty rocket plus the mass of the fuel. Okay, then, to reach the escape velocity, we will get on the left-hand side the escape velocity equals to the negative of v prime. We know the value of the escape velocity. We know the value of the v prime, and it multiplies the logarithm of m. M is when the rocket reaches the escape velocity, and in the limit we would like that to be when all the fuel is done. So the mass of the rocket will be the mass of the empty rocket over the initial mass. The initial mass, as we already said, is me plus mf. Plus, actually, subtracted by g over dm dt. dm dt is m0 over 60. So we will write 60 in the numerator, and this negative sign with this negative sign will result in this positive sign here. m0 in the denominator is me plus mf, which multiplies m, which is me, the empty rocket mass, subtracted by me plus mf. Of course, me and me will cancel out. The remaining term will be the negative of mf, and we will write it as the negative of 60g multiplying mf over me plus mf. In this term here, instead of the negative of this logarithm, we will write it as the logarithm of this argument raised to minus 1, which is the same as me plus mf over me. Now, we need to find the weight of the fuel to the weight of the empty rocket. So, this is the same as the mass of the fuel over the mass of the empty rocket. So, mf over me. This is the ratio that we are looking for. mf over me. In the argument of this logarithm, we can write it as also as 1 me over me, this is 1, plus mf over me, which is the ratio that we are looking for. But here, we also have mf and me. So we need to do an approximation here. And we know that me is much less than mf. Or in other words, the mass of the fuel is much greater than the mass of the empty rocket. So, we can do an approximation in this term and also in this term here, but it's not necessary to do the approximation in this term, because here you will have, as I already said, 1 plus mf over me. So we're going to do the approximation only in this term here. Instead of mf over the sum me plus mf, let's write it as mef over mf, which is going to be 1 at the end. So if the mass of the fuel is 100 times greater than the mass of the empty rocket, then this argument here, this ratio, will be 100 over 101. In this case, the approximation that we are going to use here will result in a 1% error, almost 1% error in this term multiplying the 60 times g. If the mass of the fuel is higher than 100, the error is going to be less than 1%. Okay, so considering this approximation, the escape velocity is approximately equal to v prime multiplying the logarithm, as we already said, 1 plus mf over me, subtracted by 60 times g multiplying mf over mf, which is equal to 1. So, if we write this term on the other side of the equation, we will get the escape velocity plus 60g over v prime, approximately equal to the logarithm of this argument. And calculating the exponential on both sides, we will get the exponential of this term approximately equal to 1 plus mf over me. And of course, mf over me is approximately equal to this exponential subtracted by 1. Let's keep this. We will see that this is not significant, but we don't know yet the value of this exponential of this term. So let's keep this minus 1 up to the end. Now, let's use R in my terminal to calculate this value. So in R, we will first introduce the escape velocity, which is 11,200 meters per second. V prime is 2.1 meters per second again, and G is 9.8 meters per second squared. Okay, then let's see this term, V escape velocity over V prime. This ratio is 5,300. What about 60G over V prime? This is only 280. So this term is the dominant term. So this is just to emphasize that if the approximation that we are doing is introducing an uncertainty here, an error, an important error here, this is not the case, because this term is not so relevant than this term, as we are going to see next. So now, the escape velocity plus 60G over V prime. This is equal to 5,600, close to this value here, when you consider only the escape velocity. Now, let's consider the exponential of this term. So the exponential of this term gives the infinity. So we have an issue here. We have a problem. The exponential of 5,600 is infinity. So let's try to find the exponential of 1,000. It's also infinity. So the exponential of, for instance, 500. This is 1.4 10 raised to 217 power. What about the exponential of 700? This is 1 10 raised to 304. And if you consider the exponential of 800, this is already infinity. So in this numerical calculation here, the computation of this value gives you infinity if the argument of the exponential is 800. And we are dealing with 5,600. So there is an issue here. And the issue is that there is an error on this value. This should not be 2.1 meters per second. Physically, there is no meaning on the velocity of the gases relative to the rocket to be only 2 meters per second. This should be much higher than this value. So actually, the correct value should be 2.1 kilometers per second. Or, in other words, V prime equals to 2,100 meters per second. So there is this error on the Goldstein book. And when you consider that, so instead of V prime to be 2.1, let's redefine that as 2,100 meters per second. And then This term, escape velocity over v, is just 5.3 and not 5,300. And this term 60g over v prime is 0.28. This argument is 5.6, and the exponential of that is 274. So that's why I mentioned that perhaps this term here is negligible, because we do have here that mf over me is approximately equal to 274 subtracted by 1. So this is approximately 273. And, of course, this is almost 300.